wasn't a marvellous night. We didn't do about our stuff. They tried to didn't quite nice. We had a it wasn't a good night. So we'll just open the next one.
September 2001's meeting of the Astronomical Society of Frankston. What I need to remind you of the year is we're all being videotaped tonight. We're going in the time capsule, so the entire meeting will be on tape, which undoubtedly will be a nice obsolete technology by the time it's over, and no one will be able to read it. Now, as usual, I'll pass around the idea and question box if you can fill that in, and also the viewing night roster if you care to actually participate in one of the school nights. I'll hand that round from the front. See you. As most of you would know, my name is Peter Skilton, and I'm the president of the society this year, and we'll go through the meeting as we normally do. Welcome to new members. I know there are a couple of new members here tonight. I believe Sebastian's in the audience, and also we have Alex Dixon, I believe, who's joined tonight. Welcome to you. And and Julian as well. I wasn't aware of that one. And what we'll do at the halfway break, when we have a bit of a tea break, is Sally Zester will actually meet up with you all and show you around. She doesn't have very much else to do during the break. I'd also like to note that Ronald Ritchie and Roger Chandler have also joined the society, and they appeared in time to get into the last edition of the newsletter, Scorpius. As well as reaching their 5-year milestone is Audrey Bolshin and Leanne and Marty Rudd. I'm not sure if Marty's here yet tonight. I'm sure he's going to be coming in time. Another reminder, please show your name tags if you have them. They're given out free to all new members, and if you are a new member, John Cleverdon who has his hand up over there, will arrange to get you your name tag for our next meeting. It certainly helps with meeting other people and then getting to know you as well. The raffle, David's organised the raffle prize, and he will actually show you what it is and hand it round. As usual, the tickets are $1 each, and we're not going to twist your arm to buy a raffle ticket, but you might be quite interested in some of these prizes.
Very special raffle tonight. I'll just say, second prize is a stargazing book, which is quite good. Third prize, little time magazine, so a couple of good items. Always donated that to a couple of videos. And so that's second and third prize. First prize is a meteorite. So $2 a ticket. And I'll pass this around. It's the Henry from the Henry meteorite, and it'll come with the meteorite. Plus, you'll get some information all about the meteorite itself. But while you're buying the raffle tickets, I will pass the meteorite around. Please don't steal it. I know that you won't get it at all. But it's not a very big piece. It's, and I'll pass it around and we'll have a look at it while we're all chatting up here. So
You will show and visualise it. So as you can see, it's distinctly metallic, so it's a nickel iron, and it weighs quite like having a lump of nickel iron there. And it's It's on the beach, so there you go.
I'll send that around.
Okay, what's on is, if you haven't picked up your what's on, they're sitting over there in the plastic holder that John Cleverdon's put together, as usual. Remember at the halfway break that the library will be open with Andrew Thornton, who will put his hand up. He's put his hand up at the back there, and also Jane McConnell, who will also put her hand up for the video, which will pick the back of their head and her hand. Right. The library actually has a new edition this month. It's been donated by the Ballarat Astronomical Society, and it's quite a nice colourful booklet about their history and the history of the stained glass windows and the telescopes in the observatory. So it's quite well written by Karenza Burke and Bill Fidian. And what I might do is I might quickly pass it round, and when it comes round to Andrew, if he snaffles it for the library. Right, in the previous month we had quite a few viewing nights. We had Blackrock Primary, actually at the Briars Education Centre, which was almost under the total cloud. Croydon Hills Primary at Camp Mannion, we had 92 there with clear skies. We had Penbank Primary at Camp Mannion, and there were 85 there, and one very keen teacher on astronomy and satellites and everything. The public night at the Briars on the 7th of September actually had 65 turn up. The room seats 45 comfortably, and we actually had 100 people booked in for that. So we were turning away people on the night or in the evening going up to it, putting them off by 1 month because we just couldn't fit them all in. So that's 2 months in a row now that we've had absolute bumper crowds wanting to get in. Any member nights conducted over the last month?
We did have one member night last month. There was a few telescopes there. Jeremy Scott was there. Neil Houston with Smith Cassegrain. Bob turned up with his new LX90. Myself and Russell Thompson turned up. Obviously anyone else. We had a really good night. It became a bit cloudy, but there was the moon was just before the first quarter. There was lots of occultation of the stars going on with the moon, and some nice deep sky objects were seen, Mars, etc., etc. So it was a good night. And the next one is this Saturday.
Thanks, David. And for the benefit of extraterrestrials that unearthed the time capsule in 100 years' time, that was David Girling. Now, quite a bit has been happening at the Briars, and Don again, do you want to mention what you say? No, Don don't want to say it. Essentially, the water is now connected to the observatory, and the electricity is connected and turned on. And the deep trenches where all the pipes and cables are laid that have been filled in, so you won't break your leg wandering around the site anymore. So it's basically all systems go now, because it means we can have power tools and that up there and get things moving along once we have plans approved for moving ahead. The working bee on September the 9th was very well attended, and we had about 8 cows wandering around on the site. Unfortunately, we actually had to herd them off the site and out the other side, so we're having quite a few problems with bovine incursion onto the site. I'm not sure if they're keen astronomers. Marty Rudd, who's not here yet, and his father have kindly donated a water tank to the society, and that's currently sitting up there. It's a big white thing, and it's currently empty, but it will be connected up shortly, we hope. The time capsule, which I've made a bit of reference to every now and again, has been donated by Peter Lowe, who isn't here yet, and is going to be buried pretty close to the autumnal equinox. That's autumn in terms of the northern hemisphere, or the vernal equinox, to be more exact. It's going to be buried sometime on this Saturday. Now, the exact moment of the equinox, actually 9 a.m. on the 23rd, but I suspect the people there for the viewing night won't stay around until 9 a.m. the next morning. If you have anything that you wish to contribute to the time capsule, please contact a committee member sometime between now and Saturday if you wish it included before the thing is actually sealed closed. I believe the opening is around 30 centimetres diameter hole, so if you can fit something through 30 centimetres, we'll put you in, or rather put something of yours in. And at the moment we have things such as newspapers, video cassettes, audio cassettes, photographs of the Briars, solar calculator, which obviously they'll pick out and think, oh, isn't this a quaint little device in 50 or 100 years' time. If you have anything else that you'd like to go in, there's plenty of room that will fit in. Indeed, it's even got quite a few papers from the last week, which will provide a very interesting snapshot for them, I would think, at the time.
There's some sheets of paper over there. If you just didn't Peter Lowe's request where people can write a message to the future, and they're over next to the what's on.
If you'd like to write a message to extraterrestrials in the future who might open the time capsule, then John says there's a diagram over, a sheet of paper over there that John Cleverdon has put together, whereby you can write a message to your counterparts in the future.
Write in Chinese.
Which will go in, write in Chinese, Japanese, Esperanto, or whatever you think. Right, social happenings. We had a visit to the planetarium. Does Sally Zeta wish to say anything? No, she doesn't wish to say anything. On September the 13th, we had 3 busfuls of people. 42 people went up to the planetarium to see Escape from Andraxis. Unfortunately, the planetarium's astronomer Tanya Hill was not there as planned. Up to that day, she was actually very keen to come and give us a bit of a pre-tour beforehand, but I'm not sure if the rather tragic events in New York and elsewhere in the United States impacted her in any way, but all of a sudden that evening she was not able to come. But nevertheless, we went ahead and trashed the place for leaving for Frankston after midnight. Thanks to Sally for actually organising that, and if you'd like to stand up and face the camera. John Cleverdon planned the route, and he wants to turn up and face the cameras. And driving the 3 getaway buses was Sally's husband Graham, Richard Pollard, who's not here tonight unfortunately because he works, and Don Leggett. And Don's going to face the camera as well. Right, there were no lunar graze expeditions or any other expeditions for the month. And I don't think there's anything on the occultation front coming up, but Dave might have some more to say about that in a little while. Since we last met, the Herald Sun put out this series on space, which some of you may have collected all the bits and pieces of them, a 12-part series. Some of them were actually quite good, and in fact I learned a few bits in there along the way. There were actually a couple of errors that I'm surprised that they didn't pick up, given the calibre of some of the people that were writing it. But if you didn't get a complete collection, you can still send off and fill in the appropriate form and send a cheque for, I think, about $1 each and pick up the missing bits and pieces. We also received during the month a couple of postcards from a former member, Ian Cuthbertson, who's wandering around in Queensland saying he's from the Astronomical Society of Frankston, and they're opening doors to observatories for him. So there's the Parkes radio telescope there that he got to have a bit of a ride on, and a few other bits and pieces there, and he says he'll be coming back soon. So I'll get Don to welcome him when he actually comes back down. Looking up there, you see Paint the Moon Red. I'm not sure if any of you have actually heard this. This is a rather noble plan on October the 27th. This is on American time. To get millions of people around the globe who actually see the moon in the sky at the time, to get out their laser pointers, you know, the red laser pointers that you get in the lecture theatre, and to actually aim it at the moon. And where you're aiming it doesn't actually show up too well, but it's that spot there. And the idea is simultaneously to fire your laser beams at the moon, and hopefully you'll be able to see the red colour. We won't worry too much about the physics of it, it's quite impossible, but there's nothing else in the story. Russell?
Now, holding a handheld laser pointer accurately enough so that even if the beam diverges, what, 1 second? Less than an arc second, it's probably going to put you high off. See a chance of hitting into the moon?
The suggestion was those who actually have a telescope actually point it down the eyepiece and come out the other side to help collimate the beam a bit more along the way.
So that's what they mentioned. If one laser is not strong enough to reach the moon, then two lasers aren't strong enough to reach the moon.
by the American Federal Aviation Authority that all these millions of laser pointers pointing skyward, especially in the current situation in the United States, with the concern about terrorists, that they might be wiping out a few of their citizens, I suspect. Right, are there any member observations to note?
Well, there's been a few Navy discovered recently, and the latest one is up near the spout of the teapot Sagittarius. It's still reasonably bright. It was a couple of nights ago, about between 7th and 8th magnitude.
Thanks. That was Bruce Tregaskis, who's going to stand up with the camera now and turn around.
Where's the camera?
Right up the back there.
Oh, I can't even see. Oh, I do.
Ken Bryant, I believe, has been looking at it as well. If you want to stand up, Ken, and squeeze in the picture. Any other member observations of note during the month? It's been a bit cloudy, hasn't it? Okay, well, we'll go into the segments, and maybe we can start with Ian first up.
Okay, well, after a month off, a couple of months before that, I'm back on deck again. I'd like to present what goes up for September 2001, a list of launches from Earth in the last roughly month and a half. We'll go back more than a month, back to August the 8th. I sort of picked this one as my cut-off. We have missed a few launches because I've been away. But I went back to August the 8th, but this is the first really interesting one in the last 6 weeks to 2 months, which was the launch of the Genesis Solar Probe. This spacecraft will sit at the L1 or Lagrange 1 point between the Earth and the Sun, about 1 million kilometres away from Earth. And this is actually the first sample return mission, the first mission that's going to be returning material from outer space since the moon missions. It's going to sit there for about a year, and it's simply going to collect solar wind, and then it is going to come back to Earth and drop down into the Mojave Desert in California, and they're going to recover the capsule from it and analyse the precise composition of the solar wind to increase their knowledge of exactly what sort of materials the Sun does actually produce. We have some data from the Apollo missions, and we have inferences from our observations and remote sensing. We don't have any recent data. Launched from Cape Canaveral, and you think, yeah, I've actually got pictures of the launches now. This is the actual Delta rocket that launched the spacecraft into solar orbit, not into Earth orbit, because it's actually orbiting the Sun and not the Earth itself. On August 10, we've had Space Shuttle mission STS-105, which was the crew rotation to the International Space Station. Rotating crew 2 with crew 3, and that went quite well with no particular dramas on this mission, and it landed safely after transferring the astronauts over. And that flight was Space Shuttle Discovery. Almost as soon as the shuttle left, the Russians launched a new cargo vessel, a Progress cargo vessel, to the International Space Station, carrying fuel, supplies, fuel, water, and so on to the station. And again, this docked without any problems whatsoever. Launched from the Baikonur Cosmodrome, the Russians' main space centre, aboard a Soyuz launcher. You can see the Russians have to contend with fairly hostile environment sometimes. The launch from Baikonur, which is actually in Kazakhstan, it's not in Russia itself. Russian military communication satellite. They didn't tell us exactly what it was, but most observers consider that it's most likely it's an early warning satellite. It went to geosynchronous orbit. Cosmos 2379, so it's the 2,379th Russian military satellite launched. Back in the 80s, the Russians were launching up to 300 satellites a year into orbit for various military reasons. They had an incredible launch rate. It's dropped right down now. They might launch 10 military satellites a year now. And as I said, it's postulated that it's an early warning satellite, probably with infrared receivers sitting over the United States or China, most likely China these days, watching for missile launches. And it was launched aboard their workhorse Proton rocket, which now is most definitely holding the record as the world's most reliable and most powerful launcher. Proton's done very well. On August 29th, we had a launch from Japan, carrying 2 experimental satellites, one of which is a mirror ball type of satellite. I do not know what the acronyms stand for. They're in Japanese, so who knows what the Japanese translation to English and back to Japanese would of these. They're in highly elliptical orbits, which means they approach closely to the Earth and then they go at about 40,000 kilometres. And they were basically used as a test for the Japanese new version of their H2 launcher. This is a picture of just before the actual launch. It's quite a powerful launcher, and most of the engines on it are equivalent to the engines on the new European Ariane 5, although it has fewer engines than the Ariane 5. Oops, that's not right. Slide mark up there. My apologies. On August the 30th, Intelsat 902 communication satellite launch. This one will be a ComSat, which means it's not a direct television broadcast satellite. About half of the satellites going into geosynchronous orbits now are television satellites to bring people pay TV, and the other half are standard telecommunication satellites that are carrying voice and data. Launched in the Kororu Launch Centre aboard the Europeans' older launcher, the Ariane 4, which is still performing very well and hasn't had any failures for some time. One launch that I've missed that actually comes after this one before I discuss this one was another launch to the International Space Station in the last few days, carrying a new docking module which will assist the Russian vehicles in docking with the International Space Station. I didn't have enough time to put it on the end of the presentation. On September the 10th we have USA 160. The term USA means an American military satellite, so it's a classified satellite. It is probably one of 2 types of satellites. Amateur observers have been tracking it for the last few weeks, and they've noticed that it's begun to basically deploy smaller sub-satellite payloads in a very similar manner to a series of satellites called the NOS, or Naval Ocean Surveillance Satellites, also classified satellites which have been tracked by amateur observers for many years now. There is some speculation that it's part of a brand new system that it does use sub-satellites, but it's part of the American Space Force Wide Area Surveillance System, which is supposed to be a system by which the United States will be able to track every aircraft on the face of the Earth simultaneously, using infrared and radar means, with a constellation of up to 200 small sub-satellites, each of them operating in a formation so that they can use triangulation techniques to detect targets.
You could have been working for the next day.
Well, it's an interesting case. You can't get the updated elements for this now. As you're probably aware, there are a large number of amateur satellite observers around the world who track US spy satellites. But there are in fact a hardcore group of about 20 who really do 90% of the work and who do all of the orbital analysis. And since the events in New York, they have publicly stated on their web groups that they will no longer be issuing any information about the position of the United States spy satellites. They're going to continue to track them and pass those elements between each other because they know each other and have met each other personally, but they will not give the data to people who they do not know personally. So the information on the US spy satellites will gradually degrade. In about 3 weeks' time, it will be very difficult to know where they are. So there will be 20 privileged observers and, of course, the US Air Force who know where they are. It was all done very hush-hush, and there were only very low-key announcements made. I do know that some of the members of this informal group are very closely connected with the US military, and I suspect that either some pressure was brought to bear or it was done voluntarily, because a great many of them are Americans, and of course they're quite patriotic. So very soon, nobody in the amateur world will know where the American reconnaissance satellites are, at least for a year, they've said.
Optically or
Optically, yeah, very easy. They're large, they're easy to see. But if you need a network across the whole world, in order to keep track of, particularly when they manoeuvre. So the idea will be is that after they manoeuvre, if you don't pick them up again within about 4 days to a week, you've basically lost them amongst the space junk. So if they do manoeuvre, which is quite likely that they'll do so in order to throw off anybody who's attempting to observe them, if they do manoeuvre, and they may already have manoeuvred, I just don't know now because I can't get any information about it, those 20 observers will know, but they won't let anybody else know. And so it's interesting that the events in New York have affected a whole range of different things. So that concludes what goes up for this month. And for prosperity's sake, to the extraterrestrials, I like to say, live long and prosper. And if you find my DNA in the time capsule, bring me back.
You'll have to leave some skin flakes in there or something.
I will. I'll rub it like that.
Thanks to Ian Paul there. The next one's going to be David Giller, and he's asked for a laser pointer. Do we have one here?
Just a question. Has there been any talk about GPS satellites going off?
No, there hasn't. I haven't heard any talk of that. That would be probably cost them more than it would because the GPS is now so relied on by civilians. They might degrade the signal back to the early 10 metre, 50 metre resolution, but I suspect not. GPS benefits a technological enemy. They're not against the technological enemy.
Not that we know.
Do you want to?
Well, we are typically having technical difficulties. I didn't even bring a video in this month. I don't have to break the lock, so I'm lucky, but I've still got a problem. Doesn't matter. Occultations for this month are pretty short on. I want to tell you just two things. One was there was an occultation about a week and a half ago, which I monitored, and please wait. And right, and it was around about 11 o'clock or something, and it was quite interesting to monitor because this is one which doesn't happen so often. You could actually follow the asteroid. Now these asteroids are not asteroids you normally chase every day. They're on the small side. This one was only 76 kilometres wide. It's about 11.5 magnitude star. Well, it's an asteroid. It looks like a star, but against the very faint background of the stars, there was a couple of in my field of view. There's a couple of stars. The main one I was looking at is 11th magnitude, and then this asteroid was about 12th magnitude, I'd say. And you could see it over a period of an hour, just sprawling along the night sky. And two reasons I really like to do these things. One is to chase down the star itself. It's not so easy just to find one individual star in the sky. So chasing down the star itself was good fun. And then I was lucky enough to see the asteroid. Unfortunately, I didn't see an occultation because the path, the shadow path where the asteroid would go in front of the star, it didn't happen quite where I was looking from. It might have been a little bit east, it might have been a little bit west, I wasn't sure. So that was an observation I did recently. There's not really many coming up in the near future that are of bright stars. I only like to mention at these sort of meetings of bright stars where people would be able to go out and find them. The 11th, 12th magnitude stars, I really think only the really experienced observers would want to go and chase those then because they're not easy. Something I've done for this Saturday, as you know, it's the time capsule and putting all the stuff in and hello to everyone and all that sort of stuff. I'm trying to think of something really good to put in that time capsule, but I might think of a bomb that'll go off in 50 years. That's what you get someone over. But anyway, we're having that time capsule thing. We're having a barbecue, and which is BYO food and drink. The barbecue we're on. We're going to smash a few bottles of champagne over the power and the water and all that sort of thing, and then it won't work anymore. So we'll get it on. We'll fix it again. And then we're just going to have a nice good time, so hopefully everyone can come, and then we're going to have a viewing night. And what I wanted to do on this viewing night, there's two interesting things that will happen on this viewing night. One is a couple of great occultations, and this is a computer program called a COL, and this is for Mornington. And what it predicts for you is this, the moon passing in front of stars, the background stars, some things off high. It's just of an interesting note. A lot of them are quite faint, not easy to see unless you've got a decent telescope. I wouldn't suggest some of those you would see in a 60mm refractor, or you might not even see in a 70mm refractor, but I think anything over a 4-inch you might be able to catch some of these. But this one here, this is in UT time, so at 24 minutes past 9, a 7.1 magnitude star will disappear, and then you can see it later on reappearing. But I thought 7.1 magnitude reappearing on the bright beam was a bit tough. But anyway, for those who might want to come and have never seen an occultation before and would like to see one, if you want to stick around till about 24 minutes past 9, you'll be able to see that one. And for those that have never ever seen one before, and I've seen a few of them, but for those that have never seen one and would really like to come along and think, oh, yes, we'll see what this is like, I'll let you monitor it through my telescope. I won't look at it, I'll put it on for you, and then you can look at it and then watch it disappear. I might even bring a radio and everything up and see if we can get you to do the actual observation. Alright, now there's a few others through the night, 10th magnitude and 9th magnitude stars, etc. Obviously these are a little bit harder to look at, but we should be able to see some of those as well. But this is the main one I thought that people might be interested in. And if you've got a telescope and you want to bring it up, which I hope you do that night, then you'll be able to monitor that as well. Only a couple more minutes. The other thing that is worth looking at this Saturday night, nothing to do with occultations, is the planet Mercury. Mercury is an object or a planet that you don't get to see too often because it always stays very close to the sun. And it's either in the morning or in the evening. And a lot of the times it just pops its little head over the horizon, and then by the time you think about it, it's gone again. At this time of the year, this apparition is very good. It's up near the star of Spica, and some of you may have seen it tonight. You might have seen in the west a couple of stars. I know Sally said to me she saw it. So Mercury and Spica are close together. So if you've never seen Mercury before, and you would like to see it through a telescope, it's nothing special. It's not a Jupiter, it's not a Saturn, it's not a Mars, it's a good opposition. But it's good to know that you've seen it before. Come along Saturday night and we'll show you that as well. So there's a whole range of things to do this Saturday. So if you ever think, oh, there's nothing to do in this astronomical sighting, come along Saturday night, there's plenty of things to do. And especially come along if you want to have a look at Mercury that you've not seen before. And I hope all those that have got telescopes will bring them along so the people that haven't got telescopes will be able to see them. That's about all for me. I finished early, so I think we're running a bit behind time. So thank you. Thank you to David Gelling. The next segment or two is by Roger Giller. And starting off with the aurora you went first, guys. Then followed by Sky for the Night, and actually with the Sky for the Night, Bob Heel has kindly put together a handout sheet for it. He's not here tonight, but what I'll do is I'll pass the handout sheet round if you wish to take one, and feel free to take it away.
Yeah, we had a rather good month this month on auroral activity. We've got a whole lot of slides, some real pretty pictures of auroras. And so after a quiet period of about mid-August, the sun was a lot more active. Moderate disturbance on August 17th to the 18th. They are observed mainly from high latitude locations in the Northern Hemisphere, and all these images that I'm going to show you are from the Northern Hemisphere. I just wanted to take a second to try and explain why this is the case. The auroras occur in an area around where this orange oval is here. That's centred around the geomagnetic pole. This is the north geomagnetic pole, which is there. The real black dot here is the north geographical pole. And this is taken at a quiet time of activity. This is satellite observations of the atmosphere, the activity in the Earth's upper atmosphere. When you get a disturbance from the sun, you get coronal mass ejection or solar wind increases and shock waves and this sort of thing. This oval expands and it comes down across this area here, which is in the northern United States, and also down here through Scandinavia and other parts of Europe. The similar situation in the southern hemisphere. There's the oval over Antarctica. When it expands, if it really expands a lot, it comes up to Tasmania and southern Australia. The rest of it is just over water anyhow. It will also extend up in South America. Taking that number away, you can draw lines of activity levels associated with this KP index. When that reaches a certain value, you expect to see auroras from that line north towards the pole. And as you can see, over Europe and Asia, as the activity level increases from 3 to 5, 3 to 5 to 7 or 9, the auroras become visible over a lot of highly populated areas. Similarly, because the oval is offset, as they come down from up over Canada and Alaska, comes right down across the main continent of the United States, the most heavily populated area of the United States. That's why we get lots of reports of auroras and lots of images of auroras. In the southern hemisphere, even at the highest activity level, it's not really likely to get very far up into South America or the other half of the world, just up into the area of southern Australia through Victoria. Just make it. Most of the southern hemisphere is not populated by people in the rural zones. So we've got all these lovely images. The August the 17th event in Finland. These are all different forms of the aurora. Some nice stars there. Same event taken on the guy from Germany. Just really pretty pictures. That one there's got a nice blue ray standing up here. Red ones. Holland, August the 18th. Denmark, some other good photographs, a bit of star trailing there on the exposures he's used. And one there, it's not a shadow, it's just there was a blank place in the aurora of this tree from the area he took it, because you said that it's the same tree, there's nothing there, no blank space above it. Just Maine and USA in the same event. These are only about 40% of the images that were around in the last month. Anyone know what those identify those? Something sort of reddish over here. Possibly could have been, it was looking northwest, so I ran out of time to sort of try and look up where it was. Shows how you can sort of take interesting aurora shots with good foreground objects as well, just to add a bit of interesting feature instead of plain shot of the sky. Just rays and curtains. Rain again. Finland is a good curtain there, different colours and sort of snaking across the sky. Some red in that one. Beautiful clouds. There a bit of cirrus clouds of interest to the photographs that you're doing. I think you said in the information coming, this sort of bright horizon up here was the last of the sunset. Sort of bright, going to come up that colour in the time exposure. But this here is definitely auroral in these vertical type formations here. It almost looks like an end of a rainbow. Estonia. It's quite a nice lot. There you can sort of see rotation around the pole. That was the solar wind speed picked up between August 21st and 22nd. Then on August 23rd, it started to drop off again. This increase in the solar wind speed gave rise to some activity, and this was photographed from Nome in Alaska, August 21st. Once again, interesting foreground with the mountains. There's also sunset light in the sky, lighting out the nose. As you mentioned, that the bright white down in the horizon was the sunset. Very powerful solar flare erupted August 25th. Photographs of the sun there, August 25th, August 27th, consider rotation. It's triggered a very strong radio blackout on the southern side of Earth. There was a coronal mass ejection associated with that, August 27th and 28th. The solar wind speed increased dramatically. There's a shock wave as a result of this coronal mass ejection, which shouldn't appear to go. It says from the Soho spacecraft, and as I see it, the time lapse of the thing, rushing away from the sun. Here the sun is a little circle in the centre. That's the occulting disk there, which takes away the brightness of the sun in the corona. You see it's rushing across the surface of the sun, the surface of the sky. When that hit, once again from Bismarck, North Dakota, some really nice auroral activity, very strong rays here on the right-hand side here. See horizon, foreground objects, a few street lights. Makes for some nice photographs of Quebec, same event, 28th August. Winnipeg in Canada, it's a nice curve. 28th in Holland. Meteor on that one. Andres. Yeah, what's with that one? 28th August. It's powerful solar flare erupted on the 10th of September. All the radio blackouts again on sunspot 1608. So stay tuned for details. I'll put out an auroral alert on the 15th of September from a number of fluctuations in the strength of the magnetic field around the Earth, and that when the planetary magnetic field turns southward, that renders the magnetosphere vulnerable to solar wind gusts and set the stage for auroras which high latitude observers accordingly spotted on September the 13th. And Dwayne Clawson in Michigan display was unremarkable. About 2 a.m. local time, I saw surprising amount of red at times. It was very close with skies and aurora, but there were storms here in Tinshaw. Its own unique characteristics, and this was no exception. Now we've got a typical American barn and around that. Some very nice auroras from Michigan, 13th of September. The foregrounds tends to make the photo. Here comes the sun, solar filament collapsed on September 17th, and likely to sweep past the Earth on September the 19th or 20th. American times. So there could be some chance of auroras in the next day or two. This latest, so the sun once again exploding out from the sun's corona, and that cloud of matter ejected in the sunlight will take the Earth. And the next day or so, so keep your eyes open for auroras. The next little bit I wanted to see later. Sky for the night. Well, maybe. Just I had to look tonight on the way up, and I noticed the moon, and next to it these two stars. I thought there's not two stars that brightness in that part of the sky this time of year normally. Sure enough, Mercury, reason why it's such a good apparition of Mercury this time when the Mercury's at greatest elongation, because the orbit of all planets approximately the same plane as the Earth's orbit ecliptic. The line of the ecliptic, which is where we see these orbits along, at not the time of equinox, which is only 2 or 3 days' time, is at its most vertical to the horizon, to the western horizon at sunset. That ecliptic, the red line there, is almost vertical. So at that time, when Mercury's at great elongation, it's also high above the horizon. If that happened in March, Mercury at the same elongation, the ecliptic would be laying right over at a very shallow angle. Should be able to show you that. Go to March, turn the line through there. There it is, over the right hand side. You see the ecliptic there? It's laying right over a very shallow angle. So although the planet can be the same elongation from the sun, it won't stand up high above the horizon. That's basically all I had to show on auroras and the sky for the month. I only found out the sky for the month last minute, so I hope I'll take that up. It was an observation I had tonight.
So the camera actually gets to see you now. And the next one I'll ask Bruce Tregaskis to come up. Any particular equipment that you wanted?
Well, if I can use this again today. Okay, well, tonight we're talking about the sun, and Roger's been giving us quite a bit about the sun, but I was out looking at it this afternoon. Is this going to work? It was a matter of observing the sun through quite a bit of hazy cloud, so it wasn't particularly clear. But there were a few spots visible there, if we can get the thing on. just a few facts that I gleaned today. I got most of these out of Vernon's book, that covers all the constellations, and there's quite a lot of information in there about all sorts of stars. But Alpha Centauri, as some of you know, is also known as Rigel Kentaurus, and it's the third brightest star after Sirius and Canopus, and it's got a magnitude of minus 0.27, so it's brighter than first magnitude. And it's a very obvious star, and as everyone knows, it's the brighter of the 2 pointers, or it's the furthest one from the Southern Cross. Now, when you look at Alpha Centauri through the telescope, as you all know, you see a very bright double star, and it's probably the best double star in the whole sky. It's certainly a very good one anyway. And the two stars are almost about the same size and brightness, but not quite. And they have, one of the brighter one has a spectrum that is called G2V, it's a G-type star, and the other one is DK1, a K-type star, which is a bit redder than the G-type star. Now, those spectral classes, various authorities give different spectral classes for them, so they don't all agree on exactly what they are. Anyway, Alpha Centauri, as you know, looks like a double star through the telescope, but in fact it's just a triple system. And as many of you know, the nearest star to us is not the two that you can see brightly, but it's another one known as Proxima Centauri, which is invisible to the naked eye. Proxima Centauri is associated with the other two stars, so it's all part of the one system. But Proxima is very much fainter and much further away. Now, Alpha 1 and Alpha 2, which are the two bright ones, they're about 4.3 light years away from the Earth, which, if you wanted in those who are used to miles, it's about 25 trillion miles, or roughly 40 trillion kilometres, so it's quite a distance away, even though it's the nearest star. Now, the distance of Alpha Centauri was first determined by Henderson at the Cape of Good Hope back in 1839, and that was only about 2 months after the first stellar parallax had been determined by F.W. Bessel when he observed 61 Cygni, and he found that he was able to determine that the star did appear to move amongst the background stars. Okay, I've got a minute there. Okay, we'll go through it a bit. Well, the two brightest stars have a period of 80 years, and the separation varies from 2 seconds of arc, which is pretty difficult to separate in a small telescope, up to 22 seconds of arc. And back in about 1957 was the minimum distance. Now, the two stars, the brightest one has a mass 1.1 times the Sun, and a diameter that's 1.07 times the Sun, so it's very similar to our Sun, although it has 1.5 times its luminosity. And the B star is a bit fainter. It has a mass that's also lighter, mass of 0.85 times the Sun, diameter of 1.2 times, and a luminosity of 0.4, so it's a little bit less than half as bright as our Sun. Now, I think that the star B has brightened since 1689 when it was first discovered. Now, Proxima Centauri, as I mentioned, is very faint. It's got an apparent magnitude of 10.7, so I need about a 3 or 4 inch telescope that we can pick it up. And it's an M-type star, so it's a reddish star, it's a red dwarf. It's also a flare star, and it's been known to flare up quite regularly. And in fact, some of us have tried to observe the flares many years ago. It goes around the other two stars in a period of about 500,000 years, because we've only observed a very small part of that orbit, so who knows exactly what the period is. Well, I think I'll have to leave it at that for now, and we'll carry on again next month. Thank you, Bill.
Thank you, Bruce. We'll call on Ian Sullivan to do his bit next, and then lastly John Giller.
just see if this will work. My pen just dropped out of my pocket, so. Now, I'm just going to talk tonight about something very basic, but possibly would be relevant to newcomers, people new to astronomy, and there would be a few here. You hear the words magnitude. Bruce just used it then. He talked about the sun. He talked about Alpha Centauri. A very common term when we talk about stars and when they are discovered, a brand new star. One of the properties of the star, a very important one, of course, is the brightness of the star, which we call magnitude. Now, we've got figures, and Bruce gave the figures of these values, magnitude. Somebody new to astronomy would immediately see when they saw a figure associated, they would see that the greater the figure, then the lesser the brightness, which sounds crazy, as you've got a situation of an inverse scale, something as the figure gets greater, the property you're measuring it gets less. Now, how did this occur? Well, it goes back a couple of thousand years with the ancient Greeks. Hipparchus, who was about 150 BC, devised it, we think. We've got fairly good authority. And it was Claudius Ptolemy who revised ancient astronomy and wrote the Almagest in 150 AD, pretty easy to remember the two, around about the dates, who actually set it in stone and confirmed that was the arrangement. That brighter stars in the sky, the stars you first see as soon as it gets dark, or it's starting to get dark, the first stars you see are first magnitude stars. After that you see second magnitude, then third magnitude, fourth magnitude, fifth and sixth. So they had categories of stars as getting less and less bright. And of course the numbers were going in the opposite direction to the brightness. Now, that went on for quite some years. We had that general approximation. It wasn't until 1856 that a British astronomer, a fellow who spent most of his working life in India, a fellow named Hobson, he's not all that well known, but you'll find him in the records. He thought, well, this is not quite good enough for modern astronomy, just having a rough first, second, third, fourth arrangement. It's better to mathematically set it out in such a way. And what he did is he reckoned that if you have your first magnitude, there's your first magnitude, and you notice on star maps that gets the bigger dot, and then the next biggest dot, and then the next one, then the next, next. You go 1, that's first, second, third, fourth, fifth, sixth. We get our magnitudes. Now, what he worked out is to have a nice round figure where you can run it from first to sixth, and reckon that first magnitude star was 100 times brighter than sixth magnitude. Because you've got 5 intervals between those stars, that's why we can break it up. You work out that if you compare a second magnitude star with the first magnitude star, then how many times brighter is the first than the second? Well, because it's not an arithmetic scale, it's a logarithmic one, we have to work it on the basis that this difference between 1 is the 5th root of 100. In other words, the number multiplied by itself 5 times yields 100. And the number, of course, works out about 2.5, because 2.5 times 2.5 is 6 1/4. 2.5 times that's about 15. 2.5 times that's about 40. 2.5 times 40 is 100. So that gives us that rough scale. So we've got a third magnitude star, compare that to a first magnitude star, a value of 3 is against a value of 1, which you'll see written on any star map. How many times brighter? It'll be 2.5 times 2.5, 6 1/4. But actually, if you want to be exact, it's 2.512. Now, once you've set that scale, of course, that means you've got to put everything else on it, and bear in mind that it's the brightness as seen from Earth, and you're talking about visible light. You're not talking about other radiation. Visible light, and has to be as seen from Earth. Although the difference between seeing from Earth and seeing from somewhere else in the solar system would be very small. Also, the situation means that you can have a naught situation, as Bruce mentioned there about Alpha Centauri. A very bright star. The value doesn't have to be positive. And you get down to -1, or -2, or go on. Now, what about the brightest thing in the sky? Of course, the sun. And the sun, on this scale, is a value of -26.5. What about the full moon? It's about -12. Now, what about going the other way? That is the limit, magnitude 6, but of course doesn't take into account polluted skies. They didn't have polluted skies in ancient Greece. They don't have them now. And of course, what we can see with the naked eye around the suburbs is not the limit, certainly not magnitude 6. It's probably 5 or even 4. But for the purpose of the exercise, we have that 7 and 8, 9, these are the sorts of stars that you'd see in a pair of binoculars. And you're getting up 12, 14 telescopes. As the aperture of the telescope, of course, diminishes, the light gathering power goes down. It gets harder and harder to see stars. About 20 is about the limit of a telescope, of a star, if it gets down up to about 20. Now, a photographic limit, of course, comes later. It's probably about 23.5. That is the faintest star that can be actually photographed through a telescope, even with a long exposure. So, ironically, you go roughly from -26.5 to +23.5. So that's the full range of the brightest thing in the sky to the faintest thing that can actually even be photographed through the biggest telescope. And we can have a look. I just took figures from a Norton's. You see the sort of figures you get. And you see the sun, -26.5. The moon, -12. Now what happens if you have a first quarter moon? A first quarter moon, what would that be? That, of course, you only got half as much light as you had with a full moon. So how many magnitudes would that bring it down to? About 1. You'll see 2.5. And if you have then a quarter of a moon, like a crescent moon, you'd have to bring it down another magnitude. So those sorts of things. Now what about Bruce is talking about the double star, the Alpha Centauri. You've got 2 stars, and one's got a bright, supposing you had 2 stars, and they are both the brightness of one, a double, and they're both the brightness of 1. What would happen then? The magnitude would be? No, it would go down, wouldn't it? Not go up. It would go down, and it would go down about 1 magnitude, because you've got double the amount of light. So naturally there's formulas to work it out. But this is apparent magnitude, bear in mind. Not absolute magnitude, talk about that another time. Absolute magnitude, you're comparing stars as bright as they actually are. This is purely in terms of what can be seen from Earth. One last thing, what about when you've got a bright star, like Sirius, a bright star and a very faint companion? Then that doesn't take into account, because the bright faint companion is drowned by the light from Sirius. And Sirius is the brightest star on that scale, gets down to -1.5, so that's the brightest star in the sky. But Sirius has a companion which was only detected about in the 1860s, simply because it's right next to a very bright star. It would be seen, it would have been seen a lot sooner had it not been near a bright star, but drowned in the light of a bright star. So you can't say that the detection of these stars is purely in terms of what the eye is capable of, but also depends on what is near them in space and how easily they can be seen and separated out. That's all for tonight.
John Cleverdon's going to give us a bit of a talk on GIS astronomy.
Talk is about GIS, or Geographic Information Systems in Astronomy. GIS is basically a mapping program connected to a database where each item on the map is also an item in the database. Most of it are used for mapping areas on Earth, but more recently some people have used them for mapping space as well. And I came across recently a couple of examples that have been used for mapping space, and so I'll show them to you tonight. The first example is an example of mapping the use of GIS for creating star charts. Now I was going to show them to you on the computer, but when I tried it on the computer earlier, Murphy's law struck and my program wouldn't work. Struck again, my friend. I can show you this later. You know, all the software at first looks just like SkyMap or Sky Globe or something like that. It's a bit different. This is where you can just turn lasers on off like you can with these programs and click on an object to get information. You can also just search for items on the map like you can with the database. And say, for example, you're a deep sky observer and you want to go out and say, have a look, search for open clusters in Sagittarius. And if you're familiar with how you work with a database, you can just say, search for open clusters in Sagittarius, say magnitude 5 and say magnitude 6, run that function and all those open clusters of that brightness in Sagittarius will be highlighted on the chart. Unfortunately, this program isn't working on the computer. I can't give an example of that, how it works. That's what it can do. Actually, one advantage of this is also these data files can be downloaded from the web for free, and there's a sample GIS viewer program that can be downloaded from the website for free as well. And I'll send the websites for these around on the Society's email list in the next couple of days, so that members who are interested can go around and download them. In fact, you can get all this. In fact, you can get all the stars down to magnitude 10 with this program. And you can also change the colours for the planets and the stars and the deep sky objects and constellation lines and all that. You can turn them on and off. You can change your location to wherever you want on Earth. Change the time as well. You can zoom in and out. Show me if that's pronounced. Can I do it now? This is the whole sky printout. at the moment, but as I said, you can download stars. Maybe it's year 10 if you're interested. Another example of how geodesists use for star charts is a website by the US Geological Survey. They've got a website in their planetary section with images of the Moon, Mars and Venus online. The article is about Mars, and here they've got images for the planet online. You can just click layers on and off with extra information, just like you can with a GIS program for information on Earth. When I was looking at the images of Venus, I could click on layers, for example. It would show where craters or volcano craters or other information like that was on the planet. So once again, I'll send the website for the Astronomical Society emails tomorrow. There's also another couple of articles just about another article about Venus here, the use of the GIS software. Also about use of GIS for a meteorite crater in Germany. I'll just leave this up the front later on for members who are interested to have a look.
And for those people 50 years or however long in the future that are wondering why this bell goes off every now and again, it's to try and keep our speakers snappy and on time as best they can. Okay, maybe we can have the raffle draw. And while you're drawing that, I'll just mention that in about a month's time, Vastrock will be held. That's the biennial get-together of amateur astronomers. This next one will be held by the ASF up at Heathcote on Saturday, Sunday, 13th and 14th of October. It's about a 3-hour drive north of here. And next month we've been told that we won't be in this theatrette, we'll be out in the classroom that we used to be in many, many years ago, because there's another function on here with the school, unfortunately. So don't be too surprised. Mr. President. Which one's mine?
Oh, we've got a white that's
Oh,
Who wants the medal?
yes.
Well done.
Yeah. So the meteorite has gone to Darren Baker, who's now joined.
Oh, has enjoyed that. Second prize for the book.
47E.
47. Mr.
Oh, that's mine.
Yeah. And that was one of us. The last one. Well done. I mean, we don't do that real.
No one, is it?
Yeah, we've got the third prize, which is how the universe will end.
21
with Mr. Bush. 21. Young Sebastian. Well done. Good on you, mate. Thank you for supporting the raffle.
Just a quick reminder that if you're interested in borrowing any of the loan instruments, please see Ken Bryce, and he'll put his hand up in the air again for you if you don't know what he looks like. If you're new, please remember that we're about to break for tea and coffee for a little while, and you're not to bring any food actually into here in the theatrette, just stay around by the kitchen area, and if you are new, Sally will come around and guide you around there appropriately. Now, before we actually go to the break, when we come back from the break, there'll be 2 sessions. Peter Lowe will be speaking on cosmology in the 20th century. 21st century. Oh, there's not much of the 21st century. And in here, and next door in the classroom, it will be next month, there'll be a video on astronauts' view of the Earth, which has been shown a couple of times over the years, but it's always been very popular, so we'll show that one again.
It's really boring, the speakers don't do much better. So that's next month or tonight?
No, that's tonight. So there are 46 here, so however you wish to split afterwards, and feel free to come and go between them. Remember, the library is open for borrowing books if you're a member, and Andrew will be around there in the classroom when the video will be shown. And before we do that, can I ask you all to come down the front and face the video camera, please? For posterity. Okay, well, that's it. Go and have your tea and coffee and reconvene here in, say, 22.
Live long and prosper.
Yes, it's on camera.
Gave him the key, the book, and walked home.
You have one now. Do you have the one-man shows? Because you can also go on the society's email address if you email address on the
So I said, look, so I've put it back in the house, but I've got keys. So she's run up and cancelled the insurance, and she's gone.
Thank you for that. That's great. There's also talking about the solicitor and going to the trade.
Good, what?
You got to leave it on. Yeah, no.
Set the video recording up for all you
How does this thing? Has anybody put it in?
Yes, yes.
Is there a particular?
determined to have a look at, say, Jupiter and Saturn, we have to get up early in the morning.
Well, what?
It was the case of I couldn't stand listening to him more, so
I got that from me for several
forward voice when I was one book there.
Your sister could know I run a password.
That is a problem with this telescope. It's a very sort of gets
Look as it is.
it's a little bit inconvenient.
Oh, you don't have that actually because you're not looking onto a network.
I know, but you've got to go through business things, he says that. You've got to go through it.
What do you run into or?
No.
No?
We're about to move to 2000s.
We've just done it, and when they say, don't you worry, you won't lose any files.
Do you wish to say something about Bill Gates for posterity?
I hope he's dead and that his head is not preserved in some museum attached to a computer.
Fair way out.
With any
Probably the videos. Is that water
Okay, everyone, I think we'll make a start. Most of you would know Peter Lowe here. He's been in society a very long time, almost since its inception, I would say, 1969, last century. Feeling old.
Yes, just as they started working on them.
And Peter's been past president in the past and has always kept a very heavy association with the society, turning up to school viewing nights. Sorry? He's always past president.
Could be a future past president.
And he's going to speak to us about cosmology. And without further ado, I'll hand over to Peter.
This telescope, I put this picture in here because I think that's the telescope we should have in our observatory. That's the only reason it's there. It has nothing to do with cosmology. I got it off the web. It's 25 inch off a society in the States, and I was rather impressed. It looks better in colour, but for some reason I didn't get it colour. The reason I wanted to talk about cosmology in the 20th century was that cosmology prior to that was fundamentally still a philosophy, religious type thing. There wasn't a lot of science. And in the 20th century, cosmology really became a science. And in that 100 years, we've gone from fundamentally knowing very, very little about the universe around us to understanding quite a lot about not only the structure of it, but the dynamics of it. So I thought it would be worthwhile just reviewing how cosmology has developed in the 20th century and where in the 21st century it's likely to go. Now, before we talk about cosmology, we need to just review a few things. First of all, I would like to ask the question, what do we mean by knowing something? When we say we know something, in scientific terms, this is quite an important question. Sorry?
Hasn't been disproved yet.
Yeah, well, that's one side of it. When we say we know something, what we mean is that we know, or we have a fact, and that fact is based around two components. One is some form of experience and some belief structure. The experience comes in the form of things through our senses, sight, touch, smell, all that sort of thing. Now, if you think about it, that is the only way that you can get information into your brain. You can have computers and telescopes and everything else, but they have to convert information into sight, touch, smells, taste, sound, whatever. Unless you count bionic ears or something like that, we currently have no other way of getting information. The belief system is our understanding of the way things are. We can have experiences where we don't understand what's going on and you get totally bewildered because you've got no reference to compare against when you experience something. On the other hand, you may believe something, but you've got no experience to prove it. And good old Eric von Däniken, who wants to play around with flying saucers, believes an awful lot of things, but he's got no evidence to prove it. Now, when we talk about scientific facts, one of the things that's fundamental in scientific work is this thing called principle of systematic doubting. Scientists don't believe anything. They doubt everything. And the reason that they doubt everything is because they can never prove something is true. All they can do is prove that something is likely. And so what they do there is they really take that fact of what we know as experience plus belief, and they can they change it a bit, and they say that knowledge or understanding is an observation, which is an experience, plus a theory, which is your belief system. You understand it when those two merge together, when the theory and the observation marry. Your observations come through instrumentation, and the thing that makes an observation a good observation, as David would tell you with his occultation work, is you want it to be quantified, you want it to be verifiable, and you want it to be published, and by published you mean it's been reviewed. Somebody's checked it and said, yep, that's good work. When you come under a theory, what a theory does is it tells you what you expect from your instrument. And again, it needs to be quantified, verifiable, and published. So the two components of your knowledge is your theory telling you what you expect from your instruments, and your instrumentation providing observations to back up your theory. Now, the thing that you look for, of course, is this connection in between, and what you look for there is some form of self-consistency. That is, the theory and the observation marry. When you've got them marrying, then at least now you've got some understanding that you can work against. When we talk cosmology, we'll see, what I'd like to talk about in the rest of the talk is, I want to talk about the observational data that we got during the 20th century, and I want to talk about some of the theory work that went on, and how this self-consistency was brought about. So, we're going to talk about
that background picture, Pete.
This is actually part of a computer simulation with a Cray supercomputer in Britain, looking at ways in which galaxies are formed from seeds in very early parts of the universe, and whether they form superclusters. And in fact, that slide will come up later in the presentation. So let's look at the observations and what we knew. Now, whenever I say what do we know, you have to say there was an set of observations, or there is a body of observational data, and there is a body of knowledge, a body of theory. And theory is changing all the time, and the observations are changing all the time. So what we know varies in time. And that's why scientists will never tell you they know something, they can just tell you that it's likely. And I guess we see that all the time, where today's facts are out of date tomorrow. So at the end of the 19th century, start of the 20th century, what did we know? First of all, we knew that the universe was a flat disk of stars. We could see this in the sky, it was the Milky Way, and we knew the distance to some stars, but we generally didn't know the scale of the thing. We also knew that we were unique and isolated. That is, that disk of stars was all there was. We also knew that the universe was made of hydrogen and helium mostly. At the end of the 19th century, the science of spectroscopy had got going. They managed to discover helium, the first element to be discovered that wasn't on Earth. So they were starting to get a feel for what it was made from. They thought the universe was static, it didn't change in time. They knew a little bit about relativity. The idea that Einstein came along and went, there's relativity, of course, is a nice story, but in fact that's not the way it happens. In fact, a fair bit of relativity was known in the 1890s, and it didn't actually come together as a complete theory until probably another 10 years later. So what didn't they know? They didn't know what stars were. They didn't know anything about the structure of the atom. They knew there were atoms, but it wasn't until about 1905 or 10 when the size of the atom was starting to be actually measured and the structure of the atom was starting to be probed. They didn't know what gravity is. So let's have a look at the critical observations that went on in the 20th century. So, first of all, in 1912, Slipher measured spectrum of nebula. Now, the telescopes of the day, they really didn't know what these fuzzy little objects were, and they were faint enough that the instrumentation of the day couldn't really allow you to analyse them. spectroscopy, although it was there, to analyse the spectrum of one of these nebula was really pushing the boundaries of the technology. And Slipher, I think, was using the Hooker telescope. He started measuring the spectrum of these fuzzy nebula. And in fact, although it says 1912, it took to 1923 to measure 41 of them. So this was quite a long exercise. What he discovered was, first of all, they had discovered already that stars had Doppler effects in their spectrum. So stars were moving around. And they were a bit surprised to also find that nebula also had a Doppler shift, so that they were moving around. And that of the 41 he measured, 33 of them were receding. In 1915 was the discovery of the first white dwarf that was mentioned by one of the speakers earlier tonight, and that was the star Sirius B. This totally confused everyone. The star itself had been observed in about 1860 or something like that. I think with a Clark refractor effect. I think it was Clark himself who discovered it. He was actually star testing the telescope. Because they were able to measure the spectrum of the white dwarf, and they knew from the fact that it was a double star and you could measure the orbital period, you could get the mass of the star. What they were able to show was that this star was extraordinarily dense. It was 36 orders of magnitude denser than any object you could find on the planet. And that totally confused everybody. So that was a bit of an enigma for a while. In 1918, Shapley, using again I think the Hooker telescope, was able to measure the distance to some of the nebula by looking for Cepheid variables. Now, Cepheid variables are stars that I've just got pages so they come up here. I just fix a page, pull back.
Modern science. You know you've got to pick up lotto prizes within 24 hours now?
Sorry?
You know you've got to pick up lotto prizes within 24 hours now? You want to just ignore the big one?
Now, Cepheid variables are stars that pulsate in a known way. They have a known relationship that the frequency of their pulsation is related to their brightness. So if we can find a Cepheid and we can measure its period and we can also measure its brightness, then we can get an estimate of its distance. And he was able to do that, and he was able to show that the Andromeda Nebula was of the order of about 1 million light years away. I think the modern figure is about 2.5 or something like that, but 1 million light years at that time was just amazing. What that was showing was that these nebula were enormous distances away. And that really started up the concept of what is known as an island universe. I need to talk about island universes. Nowadays we call them galaxies. But originally they were called island universes because they saw these things as separate universes sort of floating out there. Now, the moment you realise that these galaxies were separate things, the whole universe changed. Because, of course, now it wasn't one disk of stars that you were looking at. You can now say this is actually groups of stars floating out there. So the total view of the universe changed in one hit. So people started wanting to measure the distance to galaxies. Hubble was the first person to start doing that. What he did was he took photographs of galaxies and he compared them to the brightness of nearby stars. In fact, he used a device called a jiggle camera, where the photographic film is jiggled around while you take the photograph, and it makes effectively either a circle or a little square, and it blurs the galaxy out, and it also blurs the star out, so the images are the same size. And then he could then compare them and say, well, this one's brighter than that. And he just assumed that the galaxies were all about the same brightness, and therefore the faintest ones were further away. What he discovered was that there was a direct proportional relationship between velocity and distance, Hubble's law. Now that was mind-blowing, because this was the first time anyone had seen a cosmological law, that is a law that related to the universe as a whole. Up until that time we talked about natural laws, but this was the first time where we saw structure in the actual universe. That was extended by Sandage on the 200-inch Palomar and has since been confirmed right out to quasars with telescopes around the world. The original data, that was Hubble's original data, and you can see it's a little shaky, but there's definitely a relationship in there. And if you look a little closer, it extends out. Now, in order to explain this, we really have to look at phenomena that deals with the whole universe. You just can't deal with the local galaxy or a local cluster. You have to actually relate that to universal laws in some way. So this was an indication that the universe had some dynamics to it. In the 19th century, we saw the universe as static. Well, now we saw that there's actually things changing. In the 1930s, we saw the first theories of stellar structure, and Hoyle, who's only just died, Bondi and Thomas Gold were the people that really started to look at how stars worked. And they were the first people to be able to show that stars were effectively nuclear engines. And they could show the types of theories, types of nuclear reactions that were going on in the star itself, but they were limited in their computing. In 1930, obviously, they were limited in their computing power that they had. So these were sort of academic theories rather than quantitative theories. But by the time 1960 came along, computing powers had improved, and we started to see the first models of stellar evolution. And at that point, we started to take these theories, put them into dynamic models, and actually run stars and see how they aged and moved and predict where they would go on the Hertz-Russell diagram. We then started to be able to explain the different types of stars we could see in the sky. 1962, we saw the discovery of neutron stars. That was something that people didn't believe was really possible, but it was the first time. See, the white dwarf by now had been explained away as a star that was made up fundamentally of nuclear material. But a neutron star is a star that's fundamentally made up of subatomic particles. So we're now talking about something much more dense, and in fact the density of a neutron star is the same as the nucleus of an atom. So what this meant was that astronomers now could start to believe that you could produce objects that dense. So they started to bring these objects into their theoretical structures. 1964, we discovered the microwave, cosmic microwave background, and that was really the start of the verification of Big Bang Theory, and we're still doing an awful lot of work on that. That was the picture that was put out after the Kobe satellite had done it. I should point out that this is a bit of a fraud. This is the impression they give you here is that this is a map. It's not a map. These coloured sections are not, sort of hot areas and cold areas. This is known as a statistical distribution map. These are areas of high variance and low variance. The real discovery was that the cosmic ray background, it's not cosmic ray, the microwave background is very, very uniform. In fact, the variation in temperature from one point of the sky to another is less than 1 millionth of a degree. So it is very accurately the same temperature. Now that tells you that radiation came from something that was extremely smooth or extremely uniform in its structure. Go back. Actually, if you do a little bit of playing with a computer program, you can extract out the asymmetry in the thing, and really what that is showing is that our section of the universe is travelling either that way or this way. So what it was showing was that as far looking at the microwave background, our bit of the universe is actually moving relative to other bits. So it was not relevant in the story, but an interesting observation. If you actually then plotted out the spectrum by taking readings at different frequencies, different wave numbers, and this is the brightness, the intensity in Milligensky's per steradian. What that showed was that the radiation followed a particular curve. This is known as the black body radiation curve. It's at a temperature of 2.725 degrees Kelvin. Black body radiation comes from objects that are basically in thermal equilibrium. So what this is telling us is that radiation came from something that was basically in thermal equilibrium with its surroundings. And we don't have that in the universe today. So this is telling us that the universe was quite different at the time that was put down. In 1986, we just started discovering large-scale cosmic structures, superclusters and voids. Again, this has come about through the advent of computers. We're now able to produce databases of galaxies and their distances and their brightnesses and things like that. We can start to plot their distribution in space. And when we did that, we found that they were not uniformly spread. I tried to get a fairly decent picture, but I couldn't find one. But that one showed some of the sort of darkish, sort of lightish areas. If you go to some of the computer models where they've actually plotted out literally hundreds of millions of galaxies, you can see that they tend to run in lines, and there are literally phone structures in there. So one of the things we want to do in cosmology is to explain away what's going on there. In 1992, we discovered fluctuations in the, real fluctuations. As I said, that's a fraud. That's a picture that looked good for the newspapers, but it didn't actually tell us the story. The real story was that the background radiation variances were very, very small. Well, we actually did get a program which I believe was done in Australia. And I think that's what it's called, the boomerang. And what they did was that they looked at a small area of sky very, very closely. And they looked for specific variations in the temperature of the sky. And so what they were able to see is hot and cold spots. And the reason that you see hot and cold spots is because at the time that radiation was emitted, whatever the emitting surface wasn't totally uniform. There were small areas that were boiling and moving around, and you got little Doppler shifts. So you can imagine it was like a sort of surface of porridge where some areas are moving up and some areas are moving down. A good example is if you look at the sun and you see these the surface of the sun boiling away. Well, we think that's probably what's caused that. Now, one of the things that's rather interesting is that in looking at the universe, there was always a lot of discussion around whether in fact the universe was going to keep expanding or not, and whether in fact the base geometry of the universe was Euclidean, or whether it was had a positive or negative curvature to it. Now we've been able, because we can calculate out what it should have looked like. These are simulations of what the boomerang photographs should have looked like if you had a Euclidean flat space, or you had a positive or a negative curvature. And I don't think I'd give you three guesses as to which one it seems to be coming up with. And we now believe, not just from this, but from other reasons, that the universe in fact is flat. Like the Earth, yeah. Then in 1995, the Hubble telescope started determining the Hubble parameters much more accurately. One of the problems that we've had, those of us that can remember the 20th century, that is, one of the things we've seen in the last, 20 years is that every year, it used to be as standard joke at the end of the year when the President gave his address. He actually gave a talk about how old the universe was this year, because it kept changing. As they measured the Hubble constant, it was one year it was 200, the next year it was 50, then it was 250, and it just moved around. And what the Hubble telescope has done is been able to tie that down much more accurately. And this little thing that says video here is to remind me to try something funny. Cancel over this and control alt scope. Where? Oops. What's happening there?
You moved it instead of...
Did I?
You just dragged, yeah.
I can't do that. I can't do that. Right. This is not my talk, my computer's talk. I'm sort of playing it down here. I should have said all this up beforehand, shouldn't I? Now, zero that up. This is a set of photographs from the Hubble scope, and what it's doing is it's showing you a Cepheid variable in M100. And I'll run it again. So there's M100. The Cepheid variable is up on the left here. You'll see it will flash a blue dot. Then they bring out the actual photograph that Hubble was taken. And what it did was it monitored that particular star over a period of time and noted when it went dim and noted when it got bright. And it just noted the period of how long that took. And because they could also measure the brightness from the CCD camera, they were able to measure the distance to M100. And in doing that, they could compare that against what Hubble constant you need to achieve that distance. And so they were able to get Hubble's constant much more accurately. So we then started to see some consistency in this. So, the Hubble Space Telescope started telling us the real dimensions. Up until that time we sort of knew the dimensions, but there were problems in that we didn't know it well enough to be able to use the theories, whereas we do now. So what about the competing theories that were going on? We know, first of all, we knew that the universe was expanding. Right from the start, Hubble told us the universe was expanding. So our observations said we've got to deal with this universal expansion. And there were two basic ways that were put forward. One was steady-state theory, and in steady-state theory it assumed everything was the same, so it was static. It assumed that time, there was no time parameter in this, that the universe wasn't evolving in any way, and we assumed that it was infinite. By infinite meaning it was able to expand forever and there wasn't a boundary to it. With an expanding universe, you've got a problem straight away, and the problem is gravity. If you've got something that's expanding away, what you've got is gravity inside pulling it all back together again. And one of the things that we wanted to know was what was going to happen. Was the gravity going to be able to stop this expansion and pull it all back, or was the expansion just going to go on forever? But gravity was going to provide some sort of restraining force on the expansion. Now, in the case of steady state, they were actually assuming as the universe expanded, obviously if it's going to be static, the density of the universe is going to be constant. If it's constant, we've got to be making more matter to fill up the space that's being created as it expands. And so they're assuming that the density was kept constant by matter spontaneously appearing in space. Now, this is not such a silly thing to postulate. At the time, they weren't too sure how it would happen, but nowadays we've got reasons for believing that. It doesn't have to appear at a great rate. In order for the steady-state theory to work, we had to get something like 1 atom in the solar system per century created. So we're not talking vast amounts of matter in any small volume, but it was certainly enough to justify that expansion. The negative gravity came about because they assumed that space, empty space, still had a level of energy associated with it. And energy is matter. And so the space itself could affect the expansion of the universe. The negative gravity was to keep the thing expanding. And interestingly enough, this is starting to come back into vogue. The other one was the Big Bang. Really, we shouldn't call it the Big Bang. We really should call it evolving theories, because there were a number of Big Bang theories. But what the Big Bang said was that it was basically the same as the steady state. It just the difference was in where the matter came from. In the steady state, the matter came through spontaneous generation throughout the universe. But in the Big Bang, the material came from a single creation event. And so the universe was expanding because of its formation, because of this sudden expansion. And it is evolving. That is, it's different today from what it was when it first started. And its formation was caused by some creation. Now, the word explosion is wrong, but I couldn't think of another word. It's a creation event where there's a sudden expansion of space-time. And we'll talk about that in a second. So we were really looking now, we had all those observations that were done through the century, and we had a number, I've got 2 there are actually dozens of versions of these theories, but they were basically in those 2 camps. So, taking a big jump, we really have to ask the question, here we are, start of the 21st century, what does cosmology look like, and what are the components in cosmology? And there are 3 basic types of cosmology that are being researched at present. There's the standard model, which is the looking at galaxies, look at how the galaxies are put together and how the whole lot's expanding and where it's likely to go. With the Big Bang models, of course, they've started off from an explosion. So back in time, the universe was much smaller, much more dense. And at some point in the past, it was so dense that, in fact, we were dealing not with planets and galaxies, we were dealing with particles, subatomic particles. And if we go further back into time, the universe gets much smaller still, and it actually gets down to the size of atoms. And we start talking about quantum effects. So there's 3 different types of cosmology. And the secret is to try and get all these linked together so it's all one theory. So if we think about the standard model, the first thing that came about was that I lost my pointer. Mechanics and gravitation. Galileo really put the fundamentals of the mechanics together and showed some of the underlying physics for things moving around, and really discovered the concepts of inertial mass. And Newton put together his ideas on gravitational mass and the law of gravitation, and later we brought these together in a theory of relativity. The theory of relativity is really just a minor modification of these theories, and it just takes into account the fact that there are time delays in effects. In Newton, he assumed that gravity, we didn't actually assume anything, but the assumption, both underlying assumption in the theory was that gravitation occurred instantaneously. That if you had objects that were gravitationally interacting and you suddenly moved one, that the other one reacted to that instantly. Whereas in fact we know that that's not the case, that there is a time delay because the gravitational effect takes time to get to the other object. And relativity just applied that in a mathematical form. That was then applied to the evolving universes, the dynamic Big Bang type universes, and to steady state. Now, the vacuum energy and the cosmological constant that I put there is an area that has been looked at very closely because observations that have been done only in the last, well, they're only announced a month or two back, are suggesting that, in fact, the cosmological constant, which is how much energy there is in space, if there's no matter, if you take out all the matter, all the radiation, and look at what's left, the cosmological constant is a measure of that energy. And in relativity, it was assumed to be zero. That is, you could take space, clean out the radiation, clean out the matter, and you've got nothing left. Whereas we're now finding that, in fact, it's possible that we could, in fact, have something left, which is known as quantum energy. So that looks at the total large-scale structure of the universe. Now, if we look at the universe when it was maybe 1 million years old, 100,000 years, billion years old, so you've had this explosion, it's expanded out, there's all sorts of things that have gone on, and then at about 1 million years was when the universe had cooled down enough and its density had gone low enough that we started to see radiation starting to appear from it. If you think about the sun as a good example, the centre of the sun is radiating X-rays and things like that. We don't see those on the outside. You don't get that radiation until the outside of the sun, the conditions on the outside of the sun are such that the radiation could get away. Well, it's the same thing here. In that early part of the universe, all this energy couldn't actually escape until about 1 million years after the formation of the universe, and then it was able to get away. And that's what we see as the microwave background. So in particle cosmology, we're really talking about nuclear theory here, about the structure of particles. The first thing that came out of that, and Hoyle and Bondi and Gold were the people who were instrumental in this, were able to show how the elements were formed. We know that we got hydrogen and helium, but the question was, where did all the other elements come from? And why was there only a certain amount of helium? The helium comes from burning the hydrogen. And we know that as the universe exploded, it started off, the first elements that were being made was hydrogen, but the temperature was high enough that almost immediately started converting to helium. Now, it could only convert to helium for a short period of time because the universe is expanding and cooling. So there's a window of opportunity when that hydrogen gets an opportunity to burn, and so it produces a little bit of helium. And so you're looking in your theories to come up with a model that explains why we have the amount of helium that we've got today. So we started seeing theories on the synthesis of elements. And then the other thing we wanted to know was, in the Big Bang itself, was one, the cosmic ray, the cosmic microwave background was, what does that tell us about the structure of the early part of the universe? The missing matter, which is interesting. If we actually look at the matter that we can see in the telescope, count it and add it all up, and then say, is there enough matter to gravitationally stop it expanding and pulling it back? The answer is no. No by a long shot, by a factor of 10. Yet if we look at objects where we can gauge the amount of matter in the objects, like the rotation of galaxies and things like that, we get figures that show that there's a lot of matter missing. In fact, that factor of 10 is there somewhere. And we've yet to figure out whether in fact we have a problem with missing matter, or whether in fact the universe will stop expanding because of that cosmological constant, which is providing additional mass in the form of this vacuum energy. So we're still looking at that. Now the other one is the matter-antimatter. We know from the physics that we can see in particle physics that we can convert energy or electromagnetic radiation into mass and back again. Things like Compton scattering will do that. So you can take a positron and an electron and put them together and you get two gamma rays. Or you can get the two gamma rays of the right type, put them together, you'll get a positron and electron. You always produce the matter and the antimatter in equal quantities. And yet, in our universe, we don't have equal quantities of matter and antimatter. We've got all of one kind. What you call matter and antimatter is your own definitions, but we have all of one kind. And that means that there was some form of symmetry break in the Big Bang that favoured the production of one type of matter. And so we need to figure out what that is. And then the other one is galaxy formation. We need to know how, in the start of the Big Bang, what were the early structures that led to galaxies and clusters of galaxies. Were these seeds? I'm not sure if my next slide shows them actually. No, we're not going to those. What we want to know is what were the seeds in the Big Bang that led to the formation of galaxies? Did galaxies form first and then clusters of galaxies form? Or did we have a big ball of gas, and out of that ball of gas, that was effectively going to become a cluster of galaxies? So it was a bit like a chicken and egg arrangement. And that's important in the structure of the Big Bang, in that if it turns out that the galaxies formed first, then that means that the matter distribution in the early part of the universe was less uniform than we expected. So there were lots of seeds for producing galaxies, clusters of galaxies. And then we get down into quantum cosmology. Now, I should point out that one of the problems that we have with a lot of these theories is that they are all balanced on a knife edge. And one of the things that scientists don't like is theories that where all the special numbers all have to fit. You play the numbers game to make it work. And that usually means there's something wrong. And this is a plot in time of the scalar factor of the universe. And this is a universe that is able to collapse. So it has a big bang and then a big crunch. This is a universe that is Euclidean, and this is the universe that is open. And have a look at the numbers. The density in grams per cc is 4472259172401284017 grams per cc. That's 1.6 and that's 1.5. Out of all of that, 1 gram per cc variance is enough to convert you from a closing universe to an open universe. So the densities you're dealing with are extremely high, but very small effects have big results. That's an indication that we're probably wrong, but it shows you how sensitive the calculations are. We anticipate that when we look back into time, that is when we take our telescopes and we look really deep into the universe, we're looking back into time, that because the universe has been evolving, that what we will see is the universe at an earlier time. So we'll see young galaxies, and we'll see the universe as it was in its youth. And this was a photograph taken by Hubble. It was called the Deep Field photograph. And what they did there, and I'm going to do my little trick again. I'm not quite as good as Roger at organising these things. I'll shut this thing around. Deep Field, there's a text file. There you go. Now this shows the area that was photographed. So we saw the Big Dipper, that was the area that was photographed. They looked in there. They zoomed in onto that. So they zoomed in onto that, and they picked an area, and they took a photo. And that's what they saw. This is an area of sky that's about the size of a small crater on the moon as seen from the Earth. Right? The sort of thing we can see in our telescopes. And the actual photographs, I think, had 5,000 galaxies or something in it, but they've since taken it much deeper, and it's up in there, so 15,000 or something like that. Now, the interesting thing about this was, apart from the fact that there are lots and lots of galaxies, that there were really no peculiar galaxies. There were no young galaxies. There were all galaxies of all sorts of types and ages, which according to theory, is not supposed to be. Because the universe is never in theory, so we're going to have to change the theory. Right. So what came out of that was that when we took these deep sky, now they've taken a number of these, and they actually looked at that particular area of the sky and photographed it for a couple of weeks to get this sort of data. But every object, apart from that, every object in that field is a galaxy. And these are fully formed galaxies. It's not as if we're seeing little prototype galaxies or anything. So what that means is in this very early part of the universe, the galaxies were already well formed. And that tells us we've got to look even deeper to see early galaxies. And that was a total surprise because we were not expecting to see anything like that. This is, as Peter asked before, this is the result of a computational simulation that was looking at what would happen if galaxies were seeded in the early part of the universe at different times. So you could say, well, what if they were seeded 1 million years after the start? What if they were seeded 10 million years after the start? What would it look like today? So we were able to show that at least we could start to predict something about what that photograph was showing us. And I don't really know what the epoch was for that calculation. Now, then we got into quantum cosmology. Now, quantum cosmology is, I'd have to say, almost science fiction. At this stage, it is extremely speculative. No one would put their hand on their heart and say this has got anything to do with reality, but it's good fun to play with. And what they're trying to do is they're really trying to explain. These explain the evolution of the solar of the universe. What this is trying to do is explain why the universe formed in the first place, or how it formed. And what they're looking at is how energy can be spontaneously generated, and physicists like to see everything in balance. So they like to see if nature makes something, it makes an opposite. So everything balances. And one of the things that they look at in these quantum oscillations is that particles can spontaneously generate if they're antiparticle. Spontaneously generates at the same time. And if they do that, then they can react together and go back to nothing. So it's like producing a positive and negative. And these things spontaneously generate all the time. And we believe that at very, very small time scales and very, very small physical scales, that's happening in this room, happening everywhere. And there are two basic types of theory that are being explored. One is known as gauge theory. This is looking at fields, field structures, and trying to look at the ways in which energy can be generated out of field structures. The instanton theory is one that tries to bring time elements into it and explain away the structure in terms of turning time on. The whole thing is highly mathematical, and as I say, it's probably totally wrong, it has nothing to do with it, but it's an area that people are trying to tie in. And the reason they're looking at these areas is because it's a way of explaining that first expansion. And the universe is thought to have had a very fast expansion phase, so it didn't just expand uniformly. Very early in its formation, it had an enormously fast expansion and then slowed up. That very fast expansion phase is known as inflation. There is absolutely no theoretical reason for having inflation. It's something that's been added to theory purely to make the numbers work. So they've fiddled the theory, got the numbers to work, and then scratched their heads and said, well, all right, that works. I wonder what inflation, is that real? So they're trying to provide a link between theories of space structure and the actual inflation event. And they're doing that by looking at two ways in which inflation can occur. The chaotic inflation assumes that maybe you have like a foam, a bit like milk boiling, where you get a foam comes up, so you get a fast expansion through lots of individual space-time outbreaks. The quantum cosmology is something that Richard Feynman really tried to put together, and it was a mathematical theory based around the use of quantum gravitation, and what he was trying to do was to actually tie gravitational energy with the energy in space. And as I'll talk later, that's probably the bit that is the bit for the next century. Instantons are purely mathematical, right? We have yet to be able to figure out how to turn this maths into physical measurement, but the instanton is a mathematical structure, and this is one that Hawking's in England has proposed. And what he's proposing is that the instanton itself, the time starts at that point, and at different points in time, universes are spraying off it. And there are a number of different instantons. Instanton is just a set of mathematical formulae that have a particular set of properties. I think that's probably the best way to describe it. No intention of going into any maths. So the other method was the gauge theory, and that was really looking at what are known as phase transitions. As I said, in vacuum, you could take all the energy out, take all the matter out, all the radiation out. The question is, do you have something left? In a true vacuum, you actually have nothing left. There's no energy in that space. But in a false vacuum, there is energy there, and it's that energy. If I've got particles that are spontaneously coming into creation and then destroying themselves, and they're doing that trillions and trillions of times a second, then there is an averaged energy in the space. Right? And it's a bit like, I'm just trying to give an example, it's a bit like if I fill up a cup with water and then drain it very fast, then on average, I end up with a half a cup of water, because it's half, most of the time half the time it's full, half the time it's empty. So I have a half cup. Well, it's a bit like this, where if I'm creating matter, then I'm creating it and destroying it, so half the time I've got some matter. Now, what they think might happen is if these, they're shown here as bubbles, but they're really just multi-dimensional constructs. If these things actually got too big, they would start to link up, and there would be a transition at the boundary there where the two bubbles come together, and that would represent an expansion event. And gauge theory, you really start looking at potentials, and what this is saying is that you could have bubbles of almost universes forming in here, and they just create, destroy, create, destroy, create, destroy. But two of them bump together, and it's enough to set them off. Very rare event, but if it happens, you just get a couple of them together, and it's enough to get over that potential to start that expansion. So that's the type of thinking that's going Hold on, these movies. One of the other things that they're interested in at present is the formation of galaxies and galactic clusters. And the question is, how would a galactic cluster get to the state that it's in? And what I wanted to show you here was when we look at a galactic cluster and take a photograph of it, we are really looking at a very dynamic object. To us, it's stopped. It's just galaxies stuck in space. But in fact, it's extremely dynamic. And this is... stop it, start again. What this is a simulation that's done on a cluster of Cray computers. And what they've done is that they've put together, I think it was 17 million stars in the form of various galaxies. And then they've allowed these things to gravitationally interact over several months. And then this movie is just the outcome. And so this is what a cluster looks like if you could watch it over a period of time. And at some instant we take a photograph and say, what the hell's this thing? You know, you get a photograph like that and you say, oh right, that's a galactic cluster. But in fact you have to keep in the back of your mind, this is an extremely dynamic structure, and what you're trying to explain away is not that picture, but explain away all the things that are going on around that over long timescales. And the question is, did the cluster form first, or did the galaxy form first? Was it a lot of gas swirling around with galaxies appearing, or was it a lot of galaxies that formed into a cluster? Right, so the name of the game nowadays is that's the state of cosmology as of today. We've got three basic tenets, and somehow we've got to bring those together. So we know that's alive. We've talked about that. One of the other things that we can talk about is when we look at the cosmic microwave background, the actual form of the background that we see gives us a hint on the type of particles that were formed in that very early period in the universe. Those exotic particles we saw in the quantum cosmology. So we either had an inflation model, or we had cosmic strings, or we had magnetic monopoles, or we had textures which were effectively sound waves moving through the universe, when it was probably of the order of maybe that big. So, the history of the universe in one slide, right back at 10 to the minus 43 of a second. At periods smaller than that, we're seeing spontaneous generation of particles. We see the sudden formation of one giant particle, and it starts to expand. In that very early stage, we see those either the inflation phase or these exotic particles having an influence. Then the whole thing starts to break down, and we start to see the formation of particles and electromagnetic radiation, and you start seeing the first internal physical effects that are similar to maybe supernova type periods. Then we start to see actual particles, and after about a second, we're starting to see elements being formed. We're starting to see hydrogen being formed and nuclear burning into helium. And when we get back to around the 100,000 year mark, that's when we start to see the microwave radiation that we see as background. So there's an awful lot going on before that. And then galaxies start to form. And we expected, although the Hubble telescope is saying we're wrong, expected to see quasars in early galaxies, and then we'd see an evolution from there, but that doesn't seem to be the case. So that's the universe, and the problem we've got now is how do we make these three sets of theoretical models self-consistent? How do we get them so that that explains that, which explains that? And we don't have that yet. For the 21st century, just quickly going through it, we still need to study these quantum structures. Instanton theory is the one that everyone is rather gung-ho on at present. And the question is, was the original expansion uniform? And there's evidence to suggest now that the expansion is accelerating. What caused the large scale structures? As I say, was it the galaxies first, and then clusters, or vice versa? And if we can solve that, that tells us something about the structure of the very early part of the universe. Is the cosmological constant zero? That one there'll be a lot of work done on that in the next few years. Is the expansion changing? That's one that those two are linked. Can we achieve self-consistency in all those views that we had before? I would say no. So we've got a long way to go. And then the last question is, what is energy? And I think that's the one. I'll sit through that one. The computational stuff I showed you was from what was known as the Virgo project, which is a cluster of Cray and Origin 2000 computers in Britain. And it's a consortium of countries to pay for these things. And this is a simulation of the expected distribution that we would get of galaxies, making certain gravitational assumptions. And this was, let's say, 17 million particles computed over 3 months. You can imagine the speed these things are going, that's a lot of calculations. So we want to talk about, is the cosmological constant zero? If it's not zero, then steady state models come back into play. And it's interesting that we're getting evidence that that's the case. So in fact, good old steady state theory might actually get a bit of a revival if we find out that the observations are not matching the theory. If it is zero, then really only gravitational effects come into play and not other energies. Is it expanding? We really want to know where the missing matter is to stop that expansion or keep it going. Can we get the self-consistency going? The problem there is trying to come up with one big theory that does it. And then finally, the real question of this comes down to what do we mean by energy? Because it appears as if the universe was a single outbreak of energy, and that the total energy of the universe is probably a fixed number. It's probably constant. And what we're seeing is all that energy changing in form. It's either radiation, or it's matter, or it's work, or it's potential energy, and because energy can be converted in forms, but it can't be created or destroyed. It looks like the universe is actually an outburst of a certain quantity of energy. And what we want to know is, how did that outburst of energy occur? If we can figure that one out, then we're really, the rest of the universe is something that you can just go through the physics of the evolution. And so that's where we are. 21st century is going to see cosmology change quite dramatically, I should think. And if you think about it, the start of the century, where we knew so little, we've really come a long way. Sorry,
I was just going to ask, is there some way by which we can tell that some of the distant galaxies or clusters are antimatter, or could not be antimatter?
No, that's the problem. You can't go out there. If you go over and touch one and you blow up, you say, well, you really can't, because the properties are the same.
There may be a balance there between matter and antimatter.
Yeah, people have suggested that maybe there's galaxies of matter and galaxies of antimatter, but you then have to ask, how did they get separated?
Using the space, you have to wait an awful long time.
Yeah. frozen in time.
So what's the speed of the gravitational interactions if it was instantaneous?
It's believed to be the speed of light. Where we've been able to show the gravitational interactions in time, that it's come out at that speed.
There was an experiment like some years ago to try and measure gravitational waves, but what transpired from that? Was it successful?
They're still trying. There's a number of gravitational telescopes have been made and are being made. There's one in Western Australia which I don't think is operational yet. They're hoping they'll be able to see these effects. Personally, I think that they'll be enough. That they won't find them because of the type of interaction that they're looking for.
With you talking about those different theories on time in all those I can't even explain them. The explanations of the universe, and you're looking for one, or we're all looking for one to tie it all in.
Yeah.
You must have some suspicion of the framework of it all. Have you? Or you haven't got any idea of what needs to be.
It's a bit. The whole thing's a bit like a detective story, in that you're taking the observations of what you can see, and you're then working it backwards to see what you think it ought to have been, and then you prick your telescope out and have a look to see if that's what you see. So far that hasn't worked. So far, if you take the models and work them backwards, and then take your Hubble telescope and have a look, the two haven't come together. So they're still basically playing with theories to try and match the observations. And there's just a big argument with things like the Hubble. It's a bit hard to question it, but a lot of the observations get questioned because if the theory is actually working well in some areas, but then you find that it fails in others, people often then start complaining that the observation is wrong. That sort of fight goes on all the time. Right. Well, thank you very much. I didn't realise the time.
Thanks for that, Peter, and I can see it's almost time to open the time capsule.
I had you talk at least cosmological time.
Okay, well, on that note, I think we'll close this meeting of September 2001, and thank you very much for coming along and being movie stars for the evening. And we'll see you not in this room next month, but the one round by the library. So, thank you very much.
You want that video back?
You never know.
What she can do is almost uniformly. What she found was that, they referred to it as spiraling faster than slower on the outside. But in fact, what she found was that they rotated on different holes, and that just didn't fit in with the matter. When you looked at this variable code, it said, oh, that's the baseline. And it said, how should the rotate using Newton's law of gravity? And so they said, well, what matters is that this is in order to make it work. And they concluded that most of the matter on the galaxy wasn't there in the form of stars, wasn't visible. Now, they've since found in other ways that that's the case. For instance, in gravitational lenses, you're looking at light that's being bent by around galaxies. You can then use the gravitational lens to calculate how much matter there is in the galaxy to make it bend. And what they found was that there was a lot more matter there than they could see. So then they started saying, well, what is it? And some people said, well, maybe it's just what's a planet, or maybe it's ground dwarfs or something like that. Or black holes, yeah. But as you went through each possibility, you can find really good reasons why they weren't those. And they said, well, maybe it's just dark gas. But if there's that much dark gas, the light wouldn't go there. If it was ground dwarf.